right. So let's get started. So we're changing gears today. So we talked about permutation tests for the first two lectures, and now we want to do sort of very careful, rigorous treatment of randomization-based inference. And it's interesting on its own, and we'll look at it this way, and we'll connect to inference with linear regression this way. The way it connects to quantile regression, it equips us to tackle the question of how to do rank test-based inference, which is sort of a question that's been left, in a sense, open since we started using regression rank score. So test statistics that are of the flavor of rank tests but are not quite rank tests in quantile regression. So in a sense, the connection with quantile regression is that it equips us to tackle open questions pertaining to inference with quantile regression, but really the motivation is intrinsic. We want to think about how to do permutation type tests with observational data. So extremely foundational questions, extremely important questions. Okay, so our motivation for studying randomization tests is twofold. First, we're intrinsically motivated. We use permutation tests in applied research. Oftentimes, we're going to be unaware of the conditions necessary for exact validity. And likewise, and we'll dig deep into that today and tomorrow, often unaware of weaker conditions that could give us approximate or asymptotic validity. And so we often see what we think of as permutation tests applied either as placebo tests, which is kind of allows you to wave your hands and not be rigorous, or as a Fisher test, but Fisher test in the sense of, when I say Fisher test, I always mean that I think that the treatment has been assigned randomly, and that's where randomness comes from. But then oftentimes you'll see these placebo tests or pseudo-Fisher tests applied where we pretend that the treatment was assigned as if randomly, or your groups were assigned as if randomly when they're not, when in fact it's observational data, so men, comparing men and women, etc. And then we need to think a lot more carefully about validity and about conditioning. And so if we're in the business of running, for instance, permutation tests on observational data and we want probabilistic guarantees, then we need to be able to think correctly about randomization inference, and that means having the right notions of the permutation test, the right notions of invariance, and the right notions of conditioning. And that's the kind of clarifying all of that is the goal for today. And as I said, the second, the kind of sort of farther away motivation is we want to be able to think about regression rank score inference as the randomization test that it sort of implicitly claim it is in a rigorous way, and be able to be critical and to find solutions where the methods don't deliver what we want from them. Okay, so today our goal is define randomization tests generally. We want to get clear conditions for exact validity. We want to think about asymptotic validity. So that means we need to derive asymptotic distributions. What's the limit distribution of a permutation test? Well, it's something like what the histogram of your permuted test statistics stabilizes to. So there's going to be a conditional CLT, a permutational CLT that's going to tell us that. And then once we can talk about the asymptotics of permutation tests, that's going to allow us to talk about asymptotic validity. So can we recuperate validity of a permutation test, randomization test, at least asymptotically if it fails to be exact? When I say exact, I mean having correct coverage in small sample, and that's kind of the claim to fame of these procedures, is that we want conditions, albeit strong conditions, that are going to give us validity for given sample size for small n. So that's the main deliverable of these methods. There's two examples that we'll carry out throughout the lecture, sort of like step by step, but they'll be running examples. There'll be the one sample test for the mean, and which is going to be a sign test, and then the two sample test for equality of means, which is sort of what you may think of as A/B testing, and is the type of test procedurally that you're typically doing when you have running a Fisher test in an experiment for a policy or a drug, and you have a treatment and a control group. But we want to think about how to do that on observational data. So observational as in non-experimental. Okay. So the randomization test, produces critical values. It produces a randomization distribution as a function of the observed data. So that's different from standard frequentist tests, which get critical values from resampling. It gets its null distribution as if from sampling from the asymptotic distribution, or if you make distributional assumption, as if you were resampling the test statistic. The validity, however, so it's a bit tricky because the procedure keeps the data fixed, unlike the standard frequentist setup where you resample the test statistic under the null to get critical values. Here, the method is entirely conditional on the data, but the validity is unconditional, unlike a Fisher test. A Fisher test, 20 people show up for your experiment, and you get validity of the test conditional on those people, but unconditional on who got the treatment assignment, who was assigned treatment. So one of the things we want to do is really disentangle Fisher tests and randomization tests. The null distribution is going to be constructed by uniformly drawing enumerating transformations. So one such transformation is permutations. And the idea is that we want it to be true that under the null, we want it to be true that the distribution of the test statistic to let's say permutation of the data is invariant under the null. And so the idea is kind of obvious then. So if under the null and only under the null, my test statistic evaluated on the original data or on permuted data has the same distribution, then I can generate many different test statistics that have the same distribution under the null, and I can build a randomization distribution from which I can pick quantiles, bona fide p-values, etc. So that's going to be the idea, and we're going to have pictures and we're going to have examples to crystallize that. So the randomization test is the general case. Permutation tests and rank tests are going to obtain a special case, big cases. Okay, so let's formalize this.
Can I ask you a quick question?
Yeah.
To see how you're thinking on this problem, because do you view the bootstrap as a standard frequentist way of constructing
Yeah.
test? So in that sense, would you sense that standard frequentist test can also get critical values that depend on the observed data? Right. I mean, I understand that if you're just saying, well,
But it only works if you're mimicking the resampling distribution. So somehow this is what you're getting at.
I think two things.
Yeah.
So first of all, just say that I would say that this is standard frequentist practice because the bootstrap
Yeah.
is
Yeah.
critical values or contained regions, they depend on the
Yeah, so when standard frequentist, I think I really mean do you need to be in the resampling thought experiment and you're building and you're trying to get quantiles from the true distribution of the test statistic under the null. And so here what we're getting in the randomization distribution need not be a null distribution. So I think that's really the distinction I'm going after.
I thought maybe that the distinction was saying that the bootstrap, so if you do a test and getting critical values using the bootstrap, the critical values will depend on the observed data. Now the problem is that test, you cannot guarantee that it has any sort of finite sample value.
That's right. Yeah.
And I think that maybe that's more the distinction that you want to make, right?
But so I think the bootstrap, it works as long as you're accessing in the limit the resampling distribution. Here we're not we're relying on invariance. We're not relying on accessing the true resampling distribution of a test statistic.
Absolutely, but then I think the difference is not whether you use the data or not to build the critical values. I think
Yeah.
you can guarantee finite sample validity.
Yeah. And the conceptual difference is more about, am I getting at a true resampling distribution of the test statistic under the null, or something else that may not be a null distribution, but that's a behavior strictly under the null, so quantiles are meaningful for rejection. Yeah, okay, no, that's fine. There might be a pedagogically more efficient way of lining these up. Okay, thank you. Okay, so getting this in data. So I want to think about all of my data being some vector x. X is drawn from some probability distribution p, And I want to test the null that P is in some so calligraphic P has all the possible distributions. Omega naught is some subset. And I want to test the null that the distribution P that generated the data is in omega naught. And we're going to belabor the point here because it's quite crucial that the set of actions that I'm looking at is a group. And so the set of permutation forms a group, so that's a good example. The set of sign flip forms a group, that's a good example. And so what we're going to want, the key to make this work, is that under the null hypothesis, the distribution of our vector x will be invariant under transformation in Gn. And so the idea would be that if x is my full vector, so maybe it's in N, and I draw this vector. It has some distribution. I can kind of histogram it in multiple dimensions. If I instead draw permutation of this vector, well, I want that to have the same distribution as this. What's one easy example for making sure that these two have the same distribution? What would be one sufficient condition? Let's say on the entries of x. What does symmetric mean here?
It's, for example, axis symmetric, and G is just sign.
Yeah, so if G is sign flips and x is symmetric, well, if I do plus or minus 1 on any of the entries, each entry is symmetric, so that's fine. If G is a permutation, what would be enough? Yeah, if the components are independent, I draw x or I draw x and I reshuffle it. These two things have the same distribution. It just has is the distribution of a vector with all entries having that same. So independent and identically distributed. Yeah. Yeah. Okay. So great. So I'm going to need that. So already this should feel like strong conditions, but we're going to deliver very strong results. And so if I have that and we're going to give examples right after, but I'll build it abstractly now. So I can think of evaluating. So I have my test statistic. Maybe it's a difference in mean. So maybe I want to know if the first half of the entries are different from the second half of the entries, and my test statistic is sample average of the first half minus sample average of the second half. That'll be the case later. And I want to know if this is surprisingly big, if my realized test statistic is surprisingly big. Well, now I've told you I have a null hypothesis on with respect to which test statistics evaluated on reshufflings of the data, transformations of the data, have the same distribution as the realized test statistics. So that's under the null. In fact, we're getting a stronger result from this. It's true for the full vector of permuted test statistic. And so that's great. That's an opportunity because what can I do? So if I think of the set of all these permuted test statistics, well, I can histogram that. They're all distributed the same under the null. And so it makes sense to look at the value of the realized test statistic and ask among all these test statistics that are distributed the same, is this one surprisingly big? And so I can think about integrating to the right and providing a bona fide p-value. Right? So that's kind of the visual intuition. Building it formally, what do? So we pick all of our test statistics evaluated on permutations of the data. We get the order statistics, so we order them from T1, T2, all the way to Tm, m being the cardinality of the set of linear group actions. And then we pick the 1 minus alpha quantile of this empirical distribution. So to make life easy, let's suppose 1 minus alpha times m is an integer. So the 1 minus alpha quantile of this empirical distribution is just the kth order statistic. So if I want this to integrate to 1 minus alpha, then this would be t kx. You could call it c 1 minus alpha to make it reminiscent of usual notation. And then our test is this as accept reject decision is just asking, is the realized test statistic bigger than the 1 minus alpha quantile? If yes, I reject. If not, I fail to reject. Right? So you have your set of all the permutations. You build your set of the identities in there. You build your set of all test statistics on all permutations of the data, and you histogram that. You find the quantile in there, and you base your accept or reject decision on whether you're above or below the quantile. So, yeah. Oh.
It could not be that you chose the left side of the
Yeah, I'm just thinking that power comes from the test statistic being big. Arbitrarily, yeah.
So for simple permutation, like flipping signs and stuff like that, so I don't see, maybe it's just me, but I don't see where the variation in the test statistics comes from. If you just flip signs, you're gonna get the same test statistics.
I'll show you a sign flip in a second. Yeah, and then you can tell me if that makes sense. Okay. So okay, great. So we have a test phi. So then the object of interest is this function of x, phi x, which tells you if amongst the test statistic evaluated on all permutations of the data, you're bigger or lesser than the 1 minus alpha quantile. What can we get from this guy? Well, the test is going to deliver an exact test for a null hypothesis guaranteeing invariance of X under group actions of G. This is what we've been premising here. I'm collecting the assumption formally. So the randomization hypothesis is that it's a hypothesis such that under the null hypothesis, my randomization hypothesis is that under the null hypothesis, so under this additional hypothesis, which is the null, the distribution of X is invariant under group transformation in G. So exactly what we wrote. Gx and X have the same distribution whenever X has a distribution that is in the null set omega naught. And we definitely don't want that to be true outside of the null set because otherwise we wouldn't have power. And what does that give us? It gives us that under the null, if you have this randomization hypothesis, for a given test statistic and the phi we just built, the expectation of this test statistic, so the probability that the test statistic is 1, the probability that we reject under the null is exactly alpha for any n. So that's the really big powerful property. We get exact validity. We don't rely on asymptotic. It doesn't matter how small n is, and we don't even get that we're upper bounded by alpha for probability of type 1 error. We hit it exactly, while still having power, as we'll see. Okay, so let's take 1 second to think about this. So this is, again, very different from a Fisher test, where the validity is not conditional on the people who showed up to the experiment, but unconditional on who got the treatment. This is, think of the resampling experiment here. I'm taking the expectation over the superpopulation. So I draw all the subjects, I run the permutation test procedure, I accept or I reject. Then I go and I resample a whole new set of subjects, rerun the permutation test procedure, accept or reject, and this is telling you that you'll be rejecting a proportion alpha of the time under the null. But it's unconditional on who shows up. So if you're doing a Fisher test because you cared about controlling probability of type 1 error for specifically the subpopulation of your experiment, this is not giving you that. So the conditioning nuances are subtle but important. Okay, is the last display clear for everyone? No. Oh yeah, yes.
Okay.
Yeah.
So for every G in my group action, T of X has the same distribution of T, GX.
Yeah, and in fact, this is stronger, and yes.
And
So fix any G, draw the distribution of this guy if you draw 5 million of them, draw the distribution of this guy if you draw 5 million of them, and it's the same distribution. Yes, of course, it would be multidimensional, but
so you drew those two distributions,
yeah.
and you drew a third distribution, those forms on the right, and there, the way that you should think about that distribution is you fix an X, but that you
Yes.
reverse all G.
Exact. And that's the point from before. I'm not getting necessarily a null distribution. So fix X, enumerate the G's, histogram, need not be the same thing as fix a G, resample a bunch of X's from the original population, and plot that. These need not match.
And so is this what you were saying, is this what you mean when you were saying, this is a conditional procedure that has
Yes,
some conditional load?
exactly. Yes. Thank you. Yeah. Okay. Which makes it, like, it gives it a lot of flavor, I think. Okay, so, this is expectation of the test, probability of rejecting, because the test function phi is just the indicator for rejecting, right? Everybody's, okay. Yeah.
I started myself a question with the answer you gave.
Yeah.
So the randomness comes from the find simple. So I simply if the transformation G does not change distribution, so the permutation, the variation in test statistics under all permutation comes from the fact that you're in find simple.
The power of the procedure comes from these identically distributed test statistics having different values. Conditional on X, nothing here is random because in a sense, we're not really drawing, we're not thinking of the G's as random, we're just enumerating them. Yeah.
With X of infinite size, you get all the same test statistics. X is just a single realization.
Yes, exactly.
It's a random variable at one single realization. So
Yeah.
it's sampled from a distribution. It's
Yeah.
not going to be constant. There's no asymptotic. It's just a draw.
Yeah, and it's a tuple, so we're really going from x1 to xn. With the example, I think it's going to be quite clear. Okay, the last part of doing this abstractly. So why does this work? So what's the proof of the validity? So that's the standard proof. So we're saying, well, here we have to be careful because we're going to rely a lot on the sort of Fisher procedure intuition. But I'm saying, I want to think, well, my test picks up the quantile of the test statistic amongst the test statistic evaluated at all the permutation. So if I ask for the quantile of the test statistic evaluated at any of the permutation amongst the distribution of test statistic evaluated at any of the permutation, mechanically, I should have just alpha of them because I'm asking for quantiles of objects of the average proportion of objects that are below the alpha quantile amongst themselves. So mechanically, I want to think that this is going to be alpha.
Can I ask you just a clarification question about these? I think you didn't mention these, but probably you want to say that it's a finitely made permutation, so you might not be able to achieve exactly alpha by just...
Yeah. So
have to need to use some sort of
yeah.
randomization device, right?
So yeah, exact. So here I'm assuming to make things easier that I'm hitting an integer with minus alpha times m. That need not be true. If it's not true, then I need to allow for some randomization for tie cases. Yeah.
So
or make it a little bit more conservative and reject instead of randomizing. Yeah.
So then, just with the notation, so phi is the test statistic, but so what is the thing that you were writing there? That it's the average over the so the x now is that the x the data that you have?
Yeah, my original data. And now instead of asking, is this, instead of evaluating this and asking, is Tx above or below the 1 minus alpha quantile of all of the TGs, I'm asking for all the GXs, how many are above the 1 minus alpha quantile of all of the TGXs? So mechanically,
It's the same. You're asking the same question, right?
yeah, exact. So mechanically, I'm thinking that this is going to be alpha. There's a little subtlety there that I'll come back to in a second, but that's the standard phrasing of the proof. So once I have that, well, okay, I can just this is a constant, so I can just take expectations. The expectation goes through the sum. This is expectation with respect to P under the null. Gx and x have the same distribution, so I can forget about the G. Now I'm summing m times the same thing, so I can take out the sum and the denominator, and so I'm back with just EP phi x. So that's the proof. One-line proof, not so surprising because the assumption was so strong. But so where did we use the group assumption? I made a big deal of needing things to be a group. It's actually hidden in here. So remember our test phi x. What it's trying to do is trying to, in a sense, let's pick quantiles or verify that you're above the 1 minus alpha quantile with Tx amongst all the permuted test statistics. So in order to get mechanically that the sum of the test results for all the permuted x is alpha, we sort of want, again, I'm speaking a little bit heuristically, but we want this sum, this average of the tests evaluated at permuted data to look at the quantile of, let's say, TGX amongst the set of all, say, T prime, GX, G prime X. If I'm looking for every G and asking, are you above or below the 1 minus alpha quantile of the randomization distribution of every G, mechanically, I should have alpha of them above their own alpha quantile. Right, that's what I want, and that's our kind of Fisher test intuition for why this should be mechanically true. Okay, but that's not exactly what's happening, right? Because if phi x is looking at the randomization distribution of TGX, what's the randomization distribution that I build when I evaluate phi gx? This is going to pick the quantile of T gx, right? This is the argument, this is the argument, this is the argument, this is the argument. Amongst what randomization distribution? All the permutations of what? GX. oh, that's not what I want. I want this. I want to compare the TGXs amongst themselves to mechanically pick up your own quantile. So I need that this is the same as TG prime X G prime in G. And to get this surjectivity, this is if and only if, I need the G's to be a group. So this is where it comes from. The most innocuous part of the proof hides the critical condition. We need a group structure. Okay. The first equality.
It's used in the first equality?
Yeah.
Alpha equals expectation P? I thought that's just...
No, the first display.
Oh, it's used in the first display?
Yeah. Because the thing that's mechanically true is that if I look at how many of the TGXs are above the 1 minus alpha quantile of all of the TGXs, mechanically I have alpha of them. But the test evaluated at phi gx asks how many of the TGXs are above the 1 minus alpha quantile of this set. So I just need to make sure that this set is the same as this, and I'm going to get that if and only if I have a group. Yeah.
So I thought that just mechanically that means that phi g of x is just 1 if that specific g of x is above the threshold and 0 below. So I really thought I had that by definition.
No, yeah, I have that by definition. So the quantile of this by tautologically. So tautologically, the alpha of these guys over all G are going to be above the 1 minus alpha quantile of the same set. That's tautological. But if I start messing things up here, I'm not asking about how many of the TGXs are above the 1 minus alpha quantile of all of the TGXs. I'm asking how many of the TGXs are above the 1 minus alpha quantile of a different set. So then the thing's tautologically guaranteed. So I really need to recuperate the original set. Is that okay?
Sorry, just, yeah, no, I'll think about this, but just what is the definition of group you're using? I mean, it seems like here you're using the product of the two transformations.
Yeah, so think of these as permutation matrices.
No, but there's a definition of a group, right? You say something like a group,
Yeah.
there has to be an identity and there has to be an
Yeah, and it has to be closure. Yeah.
and it has to be closure under some operation.
Yeah. This operation.
So that operation is telling you that they're inside I see, so you're only using the closure here, the fact that if you, so the operation you're defining as some sort of composition, right?
Yeah, exact. Yeah.
And so somehow you're telling me that that line is not fully using the group structure, it's just using the closeness on the...
No, because I need surjectivity. I need that if I fix this G and I apply every G prime to G, I get back the whole group. You need all three axioms. So
Closeness and surjectivity, is that the same as saying that there's an inverse and there's an identity?
so you first okay, so the way I can show it fast, I need all three axioms, yeah, so I think yes, but I couldn't point to a result. Yeah. Okay, so let's go to our running examples. So so I should mention, so this is the proof that you see in every paper that uses this approach. The very many papers in your notes, and in the paper we'll talk about tomorrow. I give the extended version of the proof that makes this clear. So you could read those proofs side by side. Okay. Maybe.
You have less things that you want to evaluate.
Yeah.
So share.
Yeah. Yeah, maybe. Yeah. Okay, so what are things we can do? So we can do one sample test for the mean. So suppose I have my data. I got 10 observations, and I want to test that the mean is 0. So what would be one natural way to build things that have same distribution under the null? So one set of group actions is, you could write G as a matrix here, applied to the vector X, is flipping individually, flipping or not flipping, the sign of each entry of X. And if they're centered at 0 and symmetric, so if that's my null hypothesis, of course, flipping the sign, so looking at these distributions distributions in a mirror won't change anything. So, but more crucially, what I need is the full vector to be invariant. And yes, if each of its entries are symmetric, centered at 0, flipping the sign doesn't change the distribution. How do I build a test statistic? And so now this is going to get to your question. I'm going to say that Tx is just, I'm testing that the mean is 0. So a good test statistic is just the sample average. Right? If the mean is bigger than 0, this test statistic is going to be bigger than 0. You can take absolute values if I want to reject with a one-sided test. And then how do I build the null distribution? I'll say for any G, so I can think of my G here, instead of thinking of it as a matrix, I think of it as any choice of vector of zeros and ones. And depending if I have a 1 or a 0 in the ith entry, I flip or I don't flip the sign. And so since all of these are distributed the same under the null, I'm going to, all of these are going to be distributed the same under the null. In fact, the full vector of these is going to have a distribution that's invariant to who gets permuted or not. I can pick up all of these guys, and I can histogram them. Pick the 1 minus alpha quantile and ask, does my test statistic fall to the right, in which case I reject, or fall to the left, in which case I fail to reject. And I could take absolute values, of course. Okay, and then to your point, clearly, if when I flip the sign, I change the value of all of these. Imagine like the biggest xi entry, depending whether it gets a positive or a negative sign. This is going to affect the value of the test statistic. If I have a very large, if all of the xi's have a very large positive mean, it's pretty clear intuitively that my unmodified test statistic is going to tend to be bigger than the others. When I start flipping signs at random, I'm almost enforcing this null of min 0. So that's going to be good for power, because I don't do that on the realized test statistic. Okay.
So think about the same example, but now in the case in which
Yeah.
What's the area? So you apply the same technique to build the test, and
Then that's the alternative. We're testing not mean zero, and you're saying the truth is some mean mu.
taking the null is mu equals zero, the alternative is mu different than zero.
Yeah, yeah, yeah.
So I do this to
Yeah.
build the test.
Yeah.
So based on this construction, I think that this test that you're suggesting is going to have a property that is typically called unbiasedness, right? The power that you're going to get under any alternative is probably going to be above the guaranteed rate of error, which is
Yeah.
Let's say in that example, I know that the best unbiased test, I think this is correct, is the square root sample mean
Yeah.
larger than the typical threshold.
Yeah, yeah.
To control alpha. So the power of this test is going to look everywhere below that curve.
Yeah. I think you're right, but I would have to take your word for it. I'm not very cognizant of the. I don't know how much we know about the power properties of these things.
But in general, like this other thing that is also a fine example of biasness. Do we know that in general these tests are going to have that property of being unbiased, meaning
Yeah.
evaluate them at some point on the alternative?
So it was gonna get a little tricky because you're not gonna want to make these statements for since we fixed x. Somehow you're gonna want to think about you want to make the statements for any given x or not, but certainly under reasonable condition on x, unconditionally on x, you're gonna get unbiasedness. Yeah.
I'm just not sure if this is going back to the question that was being asked, where is the power of this thing coming from?
Yeah.
I mean, for me, the power is coming from the fact that the invariance that you have under the null, you don't have it under the alternative, right? Think about this in the context of this simple example.
Yeah. Yeah.
If the mean is not zero,
Yeah.
you flip this thing.
Yeah. And this is kind of enforcing mean zero on the permitted guys. That's what's gonna give you power. But that's we can see that, we can characterize that, but taking it to like quantifying power it's quite tricky. Yeah. I'm happy to think about that more. Yeah. Yeah.
In analytical, the G function, you may find different G function that
Yeah.
that's how you pick one.
Yeah, so it needs to. So here, okay. So here that's a randomization hypothesis. In this case, these are sign flips. Symmetry of the xi suffices to give us that. So you need to ask: is that something I believe in practice? And two, is that a group action that I can incorporate in my test statistic such that it's going to make sense with the test statistic I want to build, which is the sample average, and such that, to Pepe's point, when I start permuting, it creates a randomization distribution that's going to give me power, that's going to sort of not move with the alternative, such that the realized test statistic can move to the tail. So there's all these kind of engineering questions, but it's part of coming up with a test for your own problem. So it's part of the more art and science section of it. Okay, so the slightly disappointing part here is that yes, we're getting exact validity. We meant to test that the mean of the distribution was zero, but in fact we also had to assume that the data was symmetric in order for the test to control probability of type 1 error under the null. So that's not really great because you could be rejecting this when we thought we wanted to test this. So we have this little hesitation. So let's belabor that point. The strong null requires that the distribution be symmetric and guarantees that the exact one sample randomization test for the mean is valid. It's a stronger null requirement than the null hypothesis, that the mean are zero, which we intended to test in the first place. So you test the mean, but you assume symmetry. And so the concerns of false rejection because of model misspecification apply, and they're kind of a drawback. We're going to want to overcome that. Okay, what about the two sample test for the mean? So that's our second example. So I have two groups. I have the Z guys, Z1 to Zn. They're distributed according to some unknown distribution Fz. And I have the Y guys, Y1 to Ym, and they're distributed according to some Y distribution. And I'm interested in knowing if the Z guys and the Y guys have the same mean. And so I'm going to want to test that as my null hypothesis. I'm going to pick as my group the permutations. So Gx is a permutation of x. I can think of G as an n by n permutation matrix, but I can also think of it as the function from 1 to n to 1 to n that permutes the indices accordingly. So I can think of it this way. And how am I going to build the test statistic? Well, exactly the way you would expect. I want to compare the mean of two groups, so I'm gonna say I want to know, is the sample average in the first group, so for the first n entry, different from the sample average in the last m entry. So here I concatenate. I'm going to put the Z and Y in one long X vector. So that's my realized test statistic, exactly the one you thought you would use, the difference of sample mean. And then when I permute, I'm just reshuffling the indices. So a permuted test statistic, instead of taking the average of the Z guys minus the average of the Y guys, I reshuffle, and then I just take the average of the first N in this reshuffling and the last M in this reshuffling and compare the sample averages. Okay. But as we said, so we're using permutations. So if we want the permuted X to have the same distribution as the X, as a randomization hypothesis, what's going to guarantee that? You said it earlier? No, I'm permuting. So I need the vector to have the same distribution if I change the order of the observations. I need data to be IID. So in particular, that means that I need, when a Z changes place with a Y, I need the observation in that entry to have the same distribution. So I need identical distribution. So I need the distribution in group Z to be the same as the distribution in group Y. So that's tough, right? I set out to test equality of means, and then I'm told that if I want this procedure to go through, what I really need to be testing is that the entire distributions are equal.
Did you say that you needed the Z's to be dependent with the Y's?
That's assumed, yeah. It's the cardinality of the set of permutations. And big N is little n plus little m.
I read it the same way that's simulated. M is equal to n factorial. That's what you mean, right?
Yeah, no, I'm not excited about big M being big. Oh, I see, yeah. Okay, thank you. Yeah, that would look like I'm saying something important, but no. It's not very material to this slide. You can ignore it. Yeah. Okay, so you do that, and we have our theorem that tells us that as long as this is true, this test is going to have exact size under the null. In practice, for this example, what's the condition that's going to guarantee this? Well, I need the two distributions to be the same. All right, so this is a little bit annoying. We're going to have to overcome that. We're going to have to work to get better, weaker conditions, at least asymptotically, because this equality of distribution delivers us extremely strong tests, right? We never assumed that the data was Gaussian, never made any distributional assumptions, yet we got exact validity. Amazing. But we're going to have to work a little bit harder to sell this to applied folks, because we're asking people to make a stronger assumption than the scientific null, than the null they're setting out to test. That's more dramatic than what we had in the one sample case, where we only had to assume symmetry on top of our assumption on the first moment. That seems to be typical. Two sample problems are more demanding than one sample problems. Okay, so for both examples, we found our strong nulls. For the one sample test, it's sign flips, and symmetry is the strong null. For the two sample test, we use permutations, and equality of distribution is the strong null. So both strong null deliver a very strong result, but they're stringent. And so we also want to get in the business of producing a weaker null that's going to ask less, but that's going to give a little bit less. It's going to give asymptotic validity of these tests, and we can think of that as, in a sense, a robust backup, that if the strong null doesn't hold, at least if the weak null holds and the data is large enough, then you're going to get validity. Mm-hmm. I'm gonna that's exactly the question of the rest of the talk and a bit of the next one. So yeah, I'll have a I'll show you exactly how much I can relax the null. No, that's okay. So that's exactly the question I want us to be preoccupied with now. So if we want to give at least asymptotic validity, how much can we weaken the null hypothesis? Okay, but in order to talk about that, we need to talk about what does it mean to do asymptotics for this procedure, which, as you observed, are conditional. The procedure is conditional, the validity is unconditional. This makes things even more subtle, because then since the deliverable is unconditional, you kind of get the choice of whether or not you want to do the limit distribution theory conditionally or not. But I think all the intuition and the more powerful result is proceeding with a conditional CLT, a permutational CLT. So we're going to start with that. Okay, so we have this random variable, tgx conditional on x, and we can think of the g being drawn uniformly at random from gx, and ask, is there an asymptotic approximation to this distribution if we think of x as being fixed and g as being random? In a sense, as we were discussing earlier, there's not necessarily a need for randomness at all, because I can just take my tgx's, fix x, simply enumerating over g. Let's index that in n. And the length of n is also indexed. That's going to give me, for a small n, a kind of clunky histogram. When I go to the limit, and I have more and more and more data, what happened? Does this thing eventually stabilize, and hopefully stabilize to some sort of a normal? And that's going to be the case. So the more kind of pragmatic way of seeing this specialty is just, I get an x, I condition on it, the x is not too crazy. If the x is really, 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 really long, the histogram of the permuted test statistic is going to look like a normal. So that's just another instance of normal distributions being everywhere. Okay. Why are we interested in these guys? We're interested in the limit distribution of tgx. We're interested in this object for theoretical and methodological reason. That's going to be our approach for studying asymptotic robustness of the test. And so I'll be very clear about that in a second. Something we'll be critical about, I mentioned it so that we can get back to it in the conclusion, that sometimes you'll read people writing, oh, we're doing a permutation test, but we're using the asymptotic approximation to pick out the quantiles, because enumerating the permutation is too long. So for computational convenience. And we want to think about whether or not that makes sense. Okay, So, belaboring the point that this is just how my histogram stabilizes, we wanna take this slide to clarify the conceptual difference between the permutational CLT and the usual sort of Lindeberg-Feller CNT, or the frequentist, the standard frequentist central limit theorem, where we're trying to get at the resampling distribution of the test statistic. The usual frequentist central limit theorem gives us the distribution of Tx if x were drawn at random from the sum law. And so, if I have my T x n small n, and I had access to the data generating process because it's a simulation or because, I don't know, I could draw a distribution, maybe the small sample distribution. It's something, right? I can draw infinitely many, if I can simulate the x's, I can draw infinitely many of those tx's, going to have some distribution. And in the limit, the resampling distribution is going to go to some normal, to some normal distribution. And that's your usual CLT. It's just the resampling distribution, the true distribution of my test statistic when n is very large. So the permutation central limit theorem, it gives the distribution of TGXN conditional on x if I draw the G at random, but that's just tautologically the same as the histogram of TGX for every G. And we're going to be very interested in talking about how this object, let's call it R hat TGN, so that's just the distribution function related to the randomization distribution, what this object stabilizes to. Okay, so let's collect those PCLTs, those PCLT results, and then we're going to be able to talk about robustness, and I'll clarify what we mean by robustness. So in the case of the one sample test for the mean, this histogram of sample average of sign flipped entries under the null, so that's our one sample test, is going to go to a normal with variance, the variance of the underlying data. So that's, I'm not doing we might talk about the proofs tomorrow. Here I'm just collecting the results. Okay, and then for the No randomness. No randomness? No randomness.
Do you want me to think about the deterministic?
Yeah. Yeah. Yeah, exact. Yeah. So with probability 1 on x, so if I draw an x that's all 0 or all 10, then nothing's going to happen. But but with probability 1, if the original distribution of x is firmly continuous, etc., for any given x that's not crazy, as x gets really, really long, this is going to start, the histogram is going to stabilize. It's going to start looking like a normal.
Oh, sorry. So maybe because I thought you said you wanted me to think about this as the empirical CDF, as I fix x and I take draws uniformly.
Yeah, so that's the same because if I enumerate the G's or tell you can pick a G uniformly at random from this finite set, it is the same. But I think so it depends how you prefer to think about it. Yeah. So in fact, here I really want to think of the underlying theory as being a condition on x, and I look at how the histogram stabilizes. But you could be, we might talk about it tomorrow. You could be doing the theory using what's called Hovding's criteria, and then you really want to think of these as random functions inheriting the randomness from x. So you're correct. Whether or not it matters depends if you're going the PCLT way or the Hovding criteria way as a proof technique. Yeah.
and fix the big
Yeah.
subproblem
Yeah.
distribution.
Yeah.
But the way that the bootstrap deals with it is just like you're just explicit on the fact that there's a metric over the space of probability distributions, and you're just comparing the distance. It's just like one of these distributions is random.
Yeah.
And you're okay, you can say that the distance between the two goes in probability to zero as the sample size grows large, and then you just tell me what's exactly
In probability where you take the over X.
over the x.
Yeah, yeah, yeah.
Very typical standard.
Yeah.
It's like this bootstrap consistent that you can do it with
Yeah.
total variation, you can do it with
Yeah.
bounded machines.
Right. So you have the same dichotomy there. You could do it this way, or you could ask fixed X, what does the bootstrap resampling distribution stabilizes to? I think it's similar. The similar dichotomy with the nuance that here, the reason why you get away with proceeding unconditionally on X is because, or if all that you're looking to talk about at the end of the day is this, which is an unconditional object. But if I'm talking about this stabilizing, then I really want to think of X as fixed. So it's a stronger result, but also there's something like much more satisfying, I find. Yeah.
The way the result is doing what you're saying, though, because you get some result that's almost surely an X, right?
Yeah.
So it's kind of counterfiguration.
Getting those almost sure results for the bootstrap, I think it's a little bit tricky. So you can get the
Oh, so let me tell you, when you get this almost sure result, you find your distribution where you sample without a replacement. You couple with a distribution that samples with replacement, and then you go and you fetch the theorem that someone approved before for the bootstrap. So it's completely sitting on the theory for the bootstrap. Yeah, yeah. So the connection is formal. So yeah. So you're correct. Yeah. Yeah. Okay. Yeah.
Before moving ahead, could I ask two questions on the previous slide?
Yeah.
So you mentioned that, I guess the slide before that. Never mind. I didn't ask my question about the slides. You mentioned that one reason why we might want to think about, like one way to motivate randomization tests when we're thinking about asymptotic validity is that if the strong null holds, then we recover exact validity. But if it's the case that we're choosing our critical values based on the asymptotic distribution.
You think you're like 5 words away from giving away the punch in my next 2 slides. So do you want to hold this? Yeah. Because I think I know where you're going, and I just want to share in the catharsis. So okay. So yeah.
So you mentioned that one reason why we might want the asymptotic validity result is so that we don't have to enumerate across all of the G's, instead we have this closed form expression.
So I'm saying people say that.
People say
Yeah.
Okay.
So that's another punchline that I don't know if you're about to burn, but yeah.
I was going to ask, rather than thinking about the limit as n goes to infinity, can we think about this procedure of let me sample lowercase m samples of my groups uniformly at random, compute the two statistics with that m, and then send m to infinity and think about the asymptotic sequence as I approach what I would like, which is to enumerate all my
but it won't make sense as asymptotics as big M is fixed. So the result there is that you can keep exact validity if you sample uniformly at random from the group. So the like naive computationally feasible approach when there are too many permutations, that naive approach works. Just pick a random subsample and you're gonna stay valid. Yeah. Yeah.
So sigma of f is
Just the standard deviation of the original data. So I'm drawing the one sample test. I'm drawing x1 to xn from f, and I'm inquiring about whether the mean of this observation is 0.
so I guess what I was saying is like I thought that the statement was going to be the sigma of the bottom that suit over t of the r hat group that, as we discussed, it depends on x. The
Yeah. Yeah.
You're able to have convergence in probability to zero.
No, no.
What you're saying is
For almost every x. That's why I like this so much, because it's telling me that for the data that I got, this is true. I don't need to go to the casino and hope that with high probability this is happening. This is telling me, like, in real life, with the data that I can see, unless I got crazy garbage data, this is gonna hold.
so this is textbook results. So this is
Yeah, so this is directly from Romano 1990 randomization without invariance. Excellent paper. Okay, what about the PCLT? What about the PCLT for the two sample test for the mean? So right, I got sample average of the first m guys, sample average of the last m guys. The first m guys are z guys, the last m guys are y guys. I reshuffle. For every reshuffling, I compute the test statistic of whoever landed in the first n position minus the sample average of whoever landed in the m position. That's going to stabilize to some normal distribution. What will be the variance of that normal distribution? It's going to be, we're going to call it tau square. And tau square is going to be the variance of the z guys plus, so I want lambda to be m over n plus m. So the fraction of of people in the second group. And so the variance is 1 over lambda minus lambda, sigma square fy. So that's the variance when you work out the PCLT. Okay, so robustness. Now that we have these PCLTs, we can talk about asymptotic robustness. That was kind of the goal. The randomization hypothesis is that we call it a strong null for a good name. It's very strong. It might be too strong to hold. Can we get some sort of asymptotic validity under weak null? In some sense. So what is this robustness that we're talking about? If a permutation test is not exactly valid, but its PCLT yields the same distribution as the Linde-Bergfeder CLT, then what happens? What's going to happen is that, so let's, okay, we can deliver the point. What's going to happen? So remember, I have this as the true resembling distribution of the test statistic. That's its true null. So if my test statistic lands here, and I integrate to the right, that's the definition of a p-value. That's going to be a valid p-value just by definition. So this is going to be almost always a normal with some variance. Let's call it variance star. This is going to be some different distribution. If these distributions don't match, well, I'm shit out of luck, right? There's nothing I can do. But what does it mean to be robust? Imagine that this distribution, this PCL2, goes to, as here, a normal with some variance. Let's call it variance P instead of variance hat. And imagine that those variances match. So now, this randomization distribution is sampling, is going to match in the limit the true frequentist distribution. So even though I'm doing something that's wrong, even though my test statistic might not be exchangeable in the sense of having a valid permutation test, when I pick up a quantile from my randomization distribution, since I'm matching the resampling distribution, I'm inadvertently, happy mistake, happy coincidence, picking up a quantile from the true resampling distribution, and so I'm picking up a valid quantile because I'm inheriting the validity of the frequentist procedure. So the name of the game for validity is to make sure, asymptotic validity, is to make sure that your randomization distribution, even though I'm not getting exchangeability amongst the permuted test statistic, that it stabilizes to the true resampling distribution of the test statistic. If I do that, when I pick quantiles from my randomization distribution, I inadvertently pick quantiles from the true frequentist resampling distribution, and therefore I'm valid. Yeah.
So if we were to choose the quantile from the finite sample randomization
Yeah.
distribution, we know we have validity there. Is that right?
If you have the strong null, yeah. Yeah.
If you were to choose the quantile of the asymptotic randomization distribution, suppose
Which one?
So it would be that one.
Just the randomization distribution when the n is large.
Exactly.
Yeah.
If you were to choose the quantile of that, without knowing that it matched the quantile of the Lindenberg-Feller CLT distribution, is there any value in that quantile?
Are you allowing the strong null to hold or not? No.
I see. Okay. So if the strong null holds, then that quantile has value, and we can use that as a
Exact.
distribution to-
Big N, small n, any n. Yeah. Yeah. So the name of the game is we derive the Lindenberg-Feller CLT, the purple one, and we ask under what condition is the PCLT going to match the Lindenberg-Feller CLT? So we have kind of a recipe, right? So just formalizing what we said, without the strong null, we may not have that the probability of type 1 error is alpha. But we want the weak null guaranteeing that in the limit, the probability of the expectation of the test, the probability of rejecting under the null is alpha. And so we know that Tx goes to a normal distribution. Clearly, we can do a large sample frequentist test and just compare the critical value to that of the resampling distribution. Does the permutation test implement that test? Well, tautologically, yes, if the empirical distribution, so what my randomization, the histogram of my randomization distribution goes to the same limiting normal as my test statistic according to the PCLT. In that case, we're indirectly, as I said, inadvertently implementing the large sample frequentist test. So, belaboring the point one last time, because it's really key. My histogram of permuted test statistic is going to go via the PCLT to some normal, and my test statistic, just its usual resampling distribution, is going to go according to the Lindenberg-Feller CLT to some normal, and we want to ask, are they the same? If they're the same, even though the permutation test is not valid, I'm inheriting the validity of the standard frequentist resampling procedure just because I'm mimicking it. And so let's keep the color straight. So the Tx is going to go to some normal, usual conversions and distribution, F1, and that's typically going to be some normal with some variance x, and the histogram of these so let's call it R hat, which is the histogram of this permuted test statistic, is going to stabilize to some F2. Typically, that's going to be some other normal with some normal with some variance, and these guys are going to be equal if the variances match. So I need conditions that they're going to deliver this. The idea is that I want to find a weak null that delivers this validity. Okay, so let's do that. So we did for the one sample test for the mean. We collected the limit. It was just normal with the variance of the original data, and that's going to match the frequentist resampling distribution. So the weak null is just whatever regularity condition we had on the sample variance to get the CLT. So we need the boundedness of the second moments. Okay, so we we get the weak null. The weak null is essentially modulo regularity condition, the null hypothesis we want to test. So we sort of save the procedure for the one sample test for the mean. It's going to be asymptotically valid under the same condition as the standard sort of t-test type approach. Okay, more interesting, we work out the PCLT for the two sample test for the mean, the one where we reshuffle. The PCLT gave us this variance. Now we can ask for the just usual textbook Lindeberg-Feller CLT. Our two sample t-test is going to go to a normal 0, let's call the variance sigma square t. And what's sigma square t? It's 1 minus lambda over lambda, variance of the z guys, plus variance of the y guys. So I get a weak null if, so what I want to get asymptotic validity is that tau square is equal to sigma square. When is that going to be true? Right? Isn't this annoying? Z, Y, Z, Y. The weight is on a different variance term. So when are the two full variances going to be equal? There's two ways for them to be equal. Lambda 1/2, yes. So that would be a very easy way to get it, because it's kind of in our control. What's the other way? Yeah, exactly. So that's our strong law. So we have a recipe, right? This is the general recipe. Work out the PCLT, work out the CLT, look at they're both going to be normal, look at the variance formula, and extract, in terms of your problem, what would suffice to make these variances equal. So for us, we need either the two groups to have the same size, or we need the variances to be equal. So that's what we collect here. Kind of foreshadowing things to come a little bit. In a sense, this seems a little bit like a weaker requirement, because I can pick the size of the groups if I'm collecting my data, so to speak. But in a sense, this is kind of promising too. We don't like that, right? We need to assume something. We wanted to test something about the first moment. Now this is forcing us to assume something about the second moment. But this is kind of suggesting that we might enforce this and do away with a weak null beyond the null hypothesis we actually want to test. So how might I be able to do away with having to match variances? In fact, with having to match these variances. If I could somehow studentize the procedure and have it that in both regimes this goes to a 1. So I would have to somehow divide by a v hat that becomes v star in this regime, and the same v hat that becomes vp in this regime. If I can do that, then I get this weak null satisfied for free, and I have a two sample test for the mean that's completely competitive with standard frequentist procedure, because it's not requiring from me assumptions that are beyond regularity conditions, stronger than the null I want to test. So that's kind of going to be where we're going to take it next tomorrow. And that's the name of the game, because here this is great. You get exact validity, but in the real world, it's kind of a perk. What you need, the sort of sine qua non condition, is that you get asymptotic validity under conditions that are not stronger than what people are used to. And if we can get that, then we'll get in the business of new competitive methodology. Okay, so recapitulating. We're going to be right on time. Great. So you have to be. So I think when you studentize this test, the variance estimate. Now, of course, it's not invariant to permutation because that's why you get that converges to something else. So now it has to work out because it's like a pooled to sample variance estimator. It's affected by whether or not you permuted the data before, but you maintain exact validity. Yeah. Okay.
Then for the other one sample test, so the thing that was dropped from the initial requirement for the validity of the exact validity of the permutation was the symmetry, right?
Yes, exact. Which is great because then they're effectively only assuming what we wanted to test and did it all.
So what I can say is, let's say for the one sample test mean problem, the permutation test has exact validity if I have symmetry, and it's asymptotically valid under the very minor assumption that I have IID sampling and finite gain.
Yeah.
So moreover, it becomes asymptotically equivalent to the standard.
Yeah, that's how I get the validity. And the boundedness on the moment, it doesn't come from matching the variances. It comes from invoking the Lindeberg failure CLT. So any like other standard method is gonna have to satisfy that too. So we're really on competing grounds in terms of validity. So that we can talk about power. In terms of validity, we're doing strictly better than a standard frequentist procedure.
So this central limit, are you imposing the because it seems like this convergence you can get under the alternative, right?
Yeah. This is all under the null. Yeah.
So they're equivalent under the null, but you could still have different behaviors locally in terms of even local power.
Yes, that's a very good point. Yeah. Yes, that's an excellent point actually. Yeah. Yeah, that's how you know that the literature is not super crowded. Like that's a really good point, but I don't think that the paper that looks at that, I'm not sure that it exists. Okay, so recapitulating, we have this notion of a strong null. It's sufficient, it's a problem-specific, sufficient condition for the randomization hypothesis. It guarantees exact validity of the test. The weak null is a sufficient condition for asymptotic validity of the randomization test, and we have this recipe. It's whatever makes your PCLT and Lindeberg failure CLT match, and then by being a bit clever, for instance, as we'll see tomorrow, by studentizing procedures, we are able to weaken the weak null. We saw that the weak null answers the question, under what condition is the randomization test implicitly implementing the unconditional test, and tautologically, that's when the limiting distribution of the test statistic matches the shape of the histogram of the permuted test statistics. Okay. So coming back to the point we wanted to be critical about. So clearly in one direction, the asymptotic equivalence result means robustness. The permutation test is valid in the unconditional sense asymptotically under the weak null because we are inadvertently implementing the standard frequentist test in the limit. Now we were talking about some references, citing wanting to use directly the critical values of some limit distribution. So let's say the critical values given by the PCLT to pick quantiles. Critical values by the PCLT to pick quantiles and sort of to make your life easier. And so, yeah. So as long as you're using the quantiles from this procedure, and that your test is valid, it works. But then we kind of be a little bit critical because if your test is valid, you would expect to match the frequentist procedure, and you're relying on asymptotics. So at this point, why not just directly use the frequentist procedure? So the idea of using it as an approximation is a little bit poorly motivated. So that's something to think about and be critical of. Okay, conclusions. So the important takeaways, the permutation test may actually require stringent conditions in the form of a strong null for validity. We can provide weaker conditions, so a weak null, such that the permutation test is valid asymptotically without the strong null. A mature treatment of permutation tests, especially done in an applied paper, should consider both. Procedurally, we run a permutation test when we think that the strong null holds, but we have the weak null as a backup. So this is kind of, which angle do you want to see it from? Do you want to think that you have the strong null because you're mostly interested in this test being exactly valid in your small sample, and you're thinking the robustness way, well, if the strong null doesn't hold, at least if the data is big enough, I have as this backup, I have this robustness, this asymptotic validity. This is how we've been talking about it throughout the class. Maybe and we'll talk about it differently tomorrow and in the conference. Maybe a better way to pitch it to practitioners is we're giving you asymptotic validity under the conditions you're used to, but on top of that, you have this perk that if this very, very strong assumption holds, then you're getting exact validity. We're not using the t-test because it's exactly valid when the data is normal. That's nice. We're using the t-test because it works really well thanks to asymptotic guarantees. It's kind of an additional perk that you get exact validity under strong conditions. So maybe that's more the way to pitch these methods if you're trying to convince applied folks to use them. Okay, so almost right on time. So that's it for this material. Tomorrow I'm gonna want to talk about how to studentize these things, get even weaker null, maybe some nuances as to how we do the asymptotics. I'm going to try to connect. So this is all on observational data, but it's permutation tests. We run them like Fisher tests. So what's the connection with Fisher tests? I want to get a little bit into that, and I want to talk about how to do these things for regressions, when you have covariates. So over tomorrow, and kind of with some overlap with my talk in the conference, we're going to be able to explore all of that. Okay, thank you very much. Yeah.
I think I'm still not clear on this point. So we have F1 and F2 are the two sort of asymptotic distributions.
Yeah.
PCLT and CLT.
Yeah.
And we're happy if they're equal because then we recover this sort of frequentist perspective of I'm resampling stuff.
Yeah.
Kind of pretend I'm doing that.
Yeah.
And I guess I'm trying to understand if they're not equal, I still have this asymptotic distribution from the PCLT.
Yeah.
Is that just crap?
Yeah. Yeah, it's just garbage.
Okay.
Yeah.
Okay, that feels weird to me because I feel what? Yeah. Okay, but I'm okay with that.
It's a histogram of things that are not exchangeable.
Okay.
And do you want it to have meaning, or are you worried that if I don't have the assumptions that make it valid, I may not even have the assumptions that make it converge?
For what I was wondering?
Yeah.
I just wanted to understand, why can't I just do whatever I'm going to do with the asymptotic distribution that I recovered from PCLT and not worry about the Lindbergh color one?
Oh yeah, I know, because you have small n. This is not exactly valid because I need something stronger, but the TGXs are not exchangeable. And I have a bigger n, they're still not exchangeable. This might stabilize to some shape, but that doesn't help me because they're still not exchangeable. But if it magically coincides with something, the quantiles of which have validity properties, then fantastic. But I kind of need to enforce this coincidence to happen by asking for conditions that make the variances match.
Okay.
But then again, permuting things, looking at permuting things and reshuffling them, it's not so different. So to begin with, these variances are maybe not so different. So you have hope that there's going to be a way to make these things match, even though we don't have exchangeable data because I'm asking for something weaker. I don't want every one of them to have the same distribution. I never asked them to have the right distribution, but the same distribution. Now I'm asking for just the second moment of the shape to be the right one. So maybe I can get that if I massage things enough. And for us, this means picking one of these two criteria. Yeah.
Yeah, thank you.
Thank you. Yeah. Any other? Were your questions answered?
I'll ask you.
Okay. All right. Yeah.
I just want to clarify a little bit. So we have a weaker condition or weaker sufficient conditions that would imply that the PCLT would coincide with the inverse.
Yeah.
But in the case of the second example where we're testing two populations, isn't that something we can test also? If the two variances are the same, are you trying to argue a bigger argument, or are you just imposing that? I feel like itself is the problem that we can test.
So the narrative I'm proposing is if the groups are not equal, we're a little bit disappointed that we have to assume something stronger than the null we want to test. So assume equal variance on top of equal means. Okay, then you say, in practice, what can we do about that? I don't think I want to pre-test my test, but what I want to do is find a way to studentize the test statistics so that I can make those variances always one. So that's going to be the approach we're going to favor.
Instead of testing for that condition,
Yeah. We're going to do it better. We're going to enforce that it holds by modifying the test statistic. Yeah.
is there anything you can do with that equals 1/2?
We can throw data in the garbage, but that's not great. Yeah. But we can studentize, so we won't have to do any of these. Yeah. Okay, thank you very much, guys.